Johnson.
And today we're going to talk all about friction. And specifically, you guys did an investigation called The Mew of the Shoe. So what in the world does that have to do with friction?
Well, the mu is just a symbol that in physics we use, unlike in chemistry, to represent the coefficient of friction.
Right. So this is a Greek letter.
Stick in a U.
I always thought of it as a U with a tail.
Huh.
Okay. And so it's a Greek letter because there are so many symbols in science that the English alphabet isn't good enough.
Nope.
And sometimes we have to go back to the good old days, this case ancient Greek, because that's where these concepts were first derived.
Correct.
So the mu of the shoe, Greek letter, and you said represents the coefficient of friction. So this is just a number. It doesn't have any units.
Correct.
And really, it's a sticky factor. How sticky is the object? So a large mu value means that the object has a lot of stickiness to the surface. So sandpaper would have a high coefficient of friction. Ice
Would not.
would not. It would have a very low coefficient of friction.
Now, I had a student, too, instead of sticky, if that still doesn't make sense, I had a person say, like, grip.
Yeah, that's a good way to think about it. So it's a grip factor. So, yeah, I like that. So this is what you guys determined, and you did an experiment. Ready for another gem of a diagram here. It's a clown shoe, I guess. All right, so there's our shoe. Is it that bad? It's that bad.
Well, his toes must be cut off, but okay.
So there's our shoe, and what we determined in our investigation is that this is a surface-dependent feature.
Friction is.
Friction.
Okay.
See if I don't know if I spelled that right. Surface-dependent feature. Okay? So I referenced basketball players. Before a basketball player steps on the court, you see him, he steps on this funny-looking mat, and then he steps on a towel, and what he's doing is he's getting all the dust and the dirt off the bottom of his shoe to increase the friction between his shoe and the floor of the gym. Now, if he doesn't do that, there's a lot of imperfections on the bottom of the shoe, and all of a sudden he is slipping and he is sliding all over the place. So by removing that, he has increased his friction. Does that make sense?
Oh, absolutely. And
Okay.
I did get a question. Now, if the shoe is just sitting there, is there friction?
Good question. The answer to that question is no. And we're going to explain that with a free body diagram.
Okay.
Okay? So we're going to draw something that I'm very comfortable with. A free body diagram. That dot there represents everything on Earth. Sometimes even the Earth itself requires some artistic insight. That's a shoe.
All right.
Okay? Would you agree that the shoe has weight?
Yes.
Okay.
If it's on Earth, it does.
So Fg, force due to gravity, or weight. And that if it's sitting on the ground, or on a table, or on anything at all, there must be this push force up, which we have called the normal force. And this is just a response. Okay? So the normal force is equal but opposite to the weight force due to Newton's third law. And that is a huge tie in here. So, you said the shoe is just sitting there.
Right.
Is there any friction?
Right.
Okay. In order for there to be friction, there would have to be an equal but opposite force in the other direction.
Okay.
So, let's say, well, we don't have to say anything. Is there any force parallel to the surface of the ground that it's sitting on?
No, it's just sitting there.
No. So, is there any friction right now?
Nope.
No. There's no friction. So, on a flat surface, with no force, then no friction. Because of the third law.
Okay.
If we take our same basic drawing, weight of shoe down, normal force up, equal but opposite, and I start pulling on the shoe, what must be the response?
Well, one of the things that you notice is that when you start pulling on the shoe, that it either is going to move or it's not going to move.
There's some resistance.
Right.
Okay. So some of that resistance is the inertia of the shoe, which we talked about with the first law.
Mm-hmm.
But most of the resistance you're noticing is due to this other force in the opposite direction called friction. So we don't have friction until we have a pulling force trying to change the motion of the object, right? Because it's a force.
Right.
Now, there's two kinds of friction. We're going to say, in this case, that the initial speed is 0, which means
It's just sitting there.
it's just sitting there. It's not moving. In order to overcome the inertia and the friction of the shoe, you have to pull hard. Because you are overcoming a very special type of friction called static friction.
Okay.
So I've got a question. Is it easier to start an object from rest, or is it easier to keep it going?
I would say probably keep it going.
That is correct. The static friction value is always bigger than the moving friction value. So if I were to draw this arrow, these arrows would now be shorter because the pulling force is overcoming a lesser friction, in this case a moving friction. Weight and normal force are still present. You guys did this investigation where you were pulling on the shoe, and you know how much you were pulling because we had this force sensor, and there was a reading on the force sensor, right?
Right.
So there was a pull. And before you pulled, there was a weight, which you measured
Mm-hmm.
with the same force sensor.
Correct.
Okay? According to the third law, what else has to be present?
Well, there has to be an opposite force.
Sure.
Whether it's on the surface perpendicular to it, which would be the normal force.
Good.
And then since we're pulling across, there would have to be another force dealing with the frictional force.
Right. So what this brings us to is our friction equation. And friction is equal to this mu, coefficient of friction, times the normal force. Now, it is impossible to directly measure the normal force, and it's really hard to measure friction. But because of the third law, what can you tell me about friction and the pulling force?
They're equal to each other.
They have to be the same. And because of the third law, what can you tell me about the normal force with respect to weight?
It's the same.
It's got to be the same. So we can write our equation a little differently, and we can say that the pulling force is equal to the coefficient times the weight. And you can determine the coefficient between any two substances. Like an important one would be the rubber on your tires to the pavement.
Absolutely.
That's a really important one to know, and it's something that traffic engineers and people that design cars worry about all the time. The calculation isn't that hard. You just have to plug it into your calculator, and in general, of course, the coefficient of friction, if we use the black equation, would be equal to friction over normal, or if you prefer the blue one, it would be the pulling force over the weight.
Now, when you're writing in the equation, they should be mindful if they ever see a lowercase f that they're talking about friction.
Yeah, and that's a way that physicists have symbolized friction with a lowercase f. I've seen it written in other ways, but that's the most common.
I think somewhere in the sheet it has like an F with the word friction in the subscript.
Yeah, sometimes it's written like this, or it's written like this. I'm lazy, so I go with just the lowercase f.
Okay.
Now, when I talk about a pulling force or a tension or an applied force, I always capital F and then I label it,
Okay.
just so that I know what I'm talking about. The only other thing I wanted to bring up was an inclined plane. And I don't want to get into the awfulness of this, but if an object is sitting on a slope,
Okay.
okay, and it's sitting still, is friction acting on it?
It's sitting still.
Yep.
Well, if it's an inclined plane, if it's able to sit still, I would have to say that there is friction because if it's say it's a circle or a ball,
Okay.
instead of a shoe, if it's on an inclined plane, something has to be stopping it from gravity pulling it down the inclined plane.
Correct. And so gravity, you said it right, is pulling straight down, but some of the gravity is directed this way, and some of it is trying to drag it down the inclined plane. So to prevent that or to slow that from happening, there is in fact a frictional force slowing that down or preventing that motion.
Now, it's pulling it in a little of a diagonal because of the fact that if we go back to our other free body diagram, the normal force is always perpendicular to the surface in which the object is sitting, correct?
That is correct. So the normal force is equal but opposite to part of gravity, the y part, and friction is equal but opposite to the x part of gravity. And we don't want to get bogged down in
No, we
the
don't.
math of that. But what I do want to recognize is that if an object is sitting still, you can still have friction, because you brought up that student question, great question. But that inclined plane is an exception to our rule. I believe that covers friction.
Okay.
So signing off, this is Mr. White.
And Mr. Johnson.